In this video, we're going to talk about section 4.5, which is basis and dimension. For something to be a basis of a vector space, it's going to have to, the set S is going to have to be made up of linearly independent vectors that span that vector space. So this really ties in with exactly what we did in the last section with spanning sets and linear independence. Basically two sides of the same coin. So we have S is -4, 5, and we have the vector 0, 0. And we're going to see if that spans R2 since we have two-dimensional vectors here. And so we could try to find the determinant there. Would be an easy thing to do to see if it's 0, -4, 5 here, 0, 0 here, and we get that the determinant is 0, which means that it's not linearly independent. So S is linearly dependent and does not span R2. Let's look at number 11. We have S is 1, 2, 1, 0, 0, 1, and 2, 1, 0, 0, 1. I'm going to have to put I can't find the determinant of that. It's not square, right? So I'm definitely going to be able to write 1, 2 as a 1, 2 is equal to 1, 1, 0 plus 2, 0, 1. That means that they're linearly dependent. And that means that S does not span R2. So 13, have S is -6, I'm sorry, 6, -5, and 12, -10. So let's look at that. 6, -5, 12, -10 is equal to -60 plus 60 is 0, which means that they're linearly dependent. Meaning S does not span R2. Okay, so that was the first few problems that tell why it's not a basis. So let's move on to the next ones will also be the same kind, but they will be with R3. So we're going to say why these do not form a basis for R3, starting with number 15. And we have S equals set of 1, 3, 0, 4, 1, 2, and -2, 5, -2. So I'm going to take the determinant here. I'm going to set it up with each vector as a column vector. And Let's come to our calculator, second matrix, edit matrix A to be 3 by 3. We want 1, 4, -2, 3, 1, 5, 0, 2, -2. And we want second matrix math determinant, second matrix A. And it has a determinant of 0, which means that they're linearly dependent. And that means S does not span R3. Moving along to our next problem is number 19. S is equal to the set of 0, 0, 0. I already know that's a problem with the 0 vector in there. That can't help me span anything. 0, 1, 0. So we take the determinant here of this. I don't even have to guess, because if I expand on that first column, it's 0, which means that these are linearly dependent. It means that S does not span R3. So let's go ahead now and move on to number 25. 25 is a little different. It has an S that's made up of some functions. Made reference to this kind of idea before, that we don't always have to have numbers as our components here in S. And are those going to span P3, all polynomials of degree, I'm sorry, P2, all polynomials of degree 2 or less? It does not. It's missing the constant component. I can make anything that I want with the x squared component and with the x component, but I'm missing the constant component. So S is linearly dependent. And does not span P2, right? Sorry, just not linearly dependent, but S does not span P2 because it's missing the constant term, like I said. All right, let's look at number 27, which also asks us about if this spans P2, 1 plus x squared, 1 minus x squared. Now our problem is that we're missing the middle term x. We could possibly get constants. We could get our x squared term out of this, but S does not span P2. We're missing the middle term. The x took at 29, and its s is 1 minus x, 1 minus x squared, negative 1 minus 2x plus 3x squared. So I see that all the pieces parts are there. Let's see if, though the problem is that negative 1 minus 2x plus 3x squared might be a linear combination of 1 minus x and 1 minus x squared. So let's try and write it this way: 3x squared minus 2x minus 1, something with a negative x squared plus 1. I'm going to do this piece first. 1 minus x and something with 1 minus x squared, like that. Okay, so to get the 3 on this side, I need a negative 3 as my coefficient on x. I'll solve for this c right here that I would need to do that. So 3x squared minus 2x minus 1 equals 3x squared minus 3 plus, let's see, minus cx plus c. So let's bring the 3 over here and make this negative 2x plus 2 equal to negative cx plus c. So c is going to be 2. And that tells me that they are a linear combination of each other, that I could write S3 is equal to 2S1 minus 3S2. So that's 2S1 minus 3S2 minus S3 equals 0. There's a linear combination, not all zeros that equal 0, so they are linearly dependent. And that means that S does not span P2. Let's look now at number 39. Instructions there ask me to determine whether a set is a basis, and my set S is for negative 3, 5, 2. And is this set a basis for R2? That's my question. So let's go ahead and find out. For negative 3, 5, 2 is 8 minus a negative 15 is 8 plus 15 is 23. Therefore, there is a unique solution if I would augment this with zeros, where making these linearly independent. I'm sorry, that means that they're linearly independent. But the only way that I get the zero vector out of this is if C1 and C2 is 0, which is great. That's what I want, which means that S spans R2. Pick any vector that you want, and we can make it out of a linear combination of these two vectors. That's what it means for it to span. So let's go ahead and look at our last problem for today, which is number 55. Number 55 asks, is S equals the set 0, 0, 0, 1, 3, 4, 6, 1, -2, a basis for R3. So we're going to take the determinant here of this, and we get clearly that determinant is 0, which means that it's not a basis because S is linearly dependent and does not span R3. All right, that's it for this video. Pretty straightforward, very similar to what we did in 4.4. When we come back next time, we'll talk about 4.6, and that is rank of a matrix and systems of linear equations. So we'll come back next time and talk about 4.6. See you for the next video.